All right, welcome to The Explainer. Today, we are tackling what is honestly considered the most intimidating topic in all of C programming. We're talking about pointers and dynamic memory allocation. But hey, don't worry. By the end of our time together today, you're going to see exactly how these concepts aren't scary at all. In fact, they are the absolute key to unlocking incredible, uncompromised power over your computer's hardware. Okay, let's dive right into this.
So here is our roadmap for today. We'll hit variables and memory lockers, meet the pointer, the stack versus the heap, mastering dynamic memory, and finally, my favorite, arrays are just pointers. Let's get right to it.
Starting off with Section 1, Variables and Memory Lockers. Okay, so before we even touch pointers, we actually have to hit reset on how we think about standard everyday variables. We're just so used to thinking about them strictly by their names and values, right? Like you say int x equals 10, and you just think of x holding a 10. Simple. But in C, every single variable has exactly 3 attributes. Yes, it has a name, like x, and yes, it has a value, like 10, but crucially, and this is the whole secret, it also has a physical memory address, a literal physical location in your computer's RAM, which usually looks like this crazy long string of hexadecimal characters, something like 0x7FFE3482. Think of memory like a giant endless row of numbered lockers in a high school hallway. Each locker has a unique number stamped right on the front. That's the physical memory address. And inside that locker is the actual data. That's your value. When you declare a variable, C simply reserves one of these empty lockers, slaps a label on it with your variable name, and drops your value inside. You can actually see the true real-world address of that locker anytime you want just by printing it out with the %p format specifier. It's totally tangible. Which brings us nicely to Section 2. Meet the pointer. Now that we know about these physical lockers, what tool do we use to interact directly with them? Well, you're going to need 2 essential tools to really become a memory master, the ampersand and the asterisk. I like to think of the ampersand when it's placed right before a variable as the locator. It simply tells you exactly where the locker is. It hands you the exact memory address of the variable. And then we have the asterisk, which I call the extractor. Officially, it's the dereference operator. When you use the asterisk on a pointer, it actually travels to that specific address, throws open the locker door, and lets you read or completely change the value inside. Just remember, context is everything here. An asterisk is used to declare a pointer variable initially, but using it later on an already declared pointer is what actually opens the locker. Let's actually see this play out in a quick action sequence. Step 1, we declare int x equals 5. Totally normal variable. Step 2, we declare a pointer, p, and set it to the address of x using our locator, the ampersand. Now, p is pointing right at x's locker. Step 3 is where the absolute magic happens. Asterisk p equals 20. We use our extractor to physically open the locker that p is pointing to and swap that old 5 out for a fresh 20. Now look at step 4. When we go to print the original variable x, boom, the output is 20. So the massive takeaway here is that changing the value through the pointer actively changes the original variable, simply because they are both talking about the exact same physical locker. All right, Section 3, the stack versus the heap. So we know how to target memory now, but where exactly in the computer is this memory even coming from? Well, there are basically 2 completely different battlegrounds. First, you have the stack. This is used for static allocation. When you just write int x equals 10, it gets thrown on the stack. It's incredibly fast, and the computer manages all of it automatically for you. But there is a massive limitation here. Its size is rigidly fixed at compile time. You absolutely must know exactly how much memory you need before the program even runs. Then, on the other side, there's the heap. This is your dynamic allocation zone. It's a massive, sprawling pool of flexible memory that you can claim while the program is actively executing. It's perfect for really large or shifting amounts of data. But, as we'll see in a second, it requires you, the programmer, to step up and manually manage the whole operation. Let's dig deeper into that in Section 4, Mastering Dynamic Memory. So how do we actually break free from the strict, rigid limitations of the stack and utilize the heap? I mean, picture this. You're building a program that processes user data, but you have no earthly idea if the user has 5 items or 5 million items until they actually boot up the app. If you stick to the stack, you basically just have to guess. Guess too low, and your program straight up crashes. Guess too high, and you're hogging wasted memory. This right here is exactly why dynamic memory on the heap isn't just a nice to have. It's an absolute necessity for real-world applications. It gives you the ultimate flexibility. So enter your new best friend, malloc. That stands for Memory Allocate. When you call malloc, you are actively raising your hand and asking the operating system to reserve a specific, custom block of bytes on the heap for you, right at runtime. You literally just tell it exactly how many bytes you need, which you usually do by taking the number of items you want and multiplying it by the size of the data type. Then malloc goes out, finds the space, and hands you back a pointer to the start of that brand new, custom-sized memory block. It's brilliant. But look, with great power comes great responsibility, right? Since the computer doesn't automatically clean up the heap for you, if you claim memory and forget to give it back, you create what's known as a memory leak. And honestly, think of a memory leak like a ticking time bomb. Your program just keeps blindly asking for more and more space on the heap, never releasing the old space it's done with. Over time, your program aggressively consumes all available RAM until the entire system literally just chokes, freezes, and crashes. To prevent those catastrophic crashes, you absolutely must burn this fundamental golden rule of C programming into your brain right now. Every malloc must have a matching free. One claim, one release. No exceptions. The free function explicitly tells the operating system, hey, I'm totally done with this memory locker. You can go ahead and let someone else use it now. It perfectly optimizes your memory usage and keeps your program stable long-term. Just a pro tip, literally never write a malloc without simultaneously planning your free.
Moving to our final part, Section 5. Arrays are just pointers.
This is where the whole thing just clicks together, and honestly, it's probably the biggest revelation of this entire explainer. To truly understand arrays, we first have to wrap our heads around pointer arithmetic. In C, pointers are surprisingly smart. They are type-aware. An integer, for example, typically takes up exactly 4 bytes of physical memory. So if you have a pointer to an integer and you add 1 to that pointer, C doesn't just bump forward by a single measly byte. Oh no! It knows it's looking at integers, so it automatically jumps forward by exactly 4 bytes to perfectly find the start of the next integer. It handles all that underlying tedious math completely invisibly. Okay, get ready for the ultimate plot twist. When you create an array in C, the name of the array isn't just a convenient label. It is literally just a pointer to the memory address of the very first element, period. So when you casually type R*1 to get the second item, those square brackets are genuinely just disguised pointer arithmetic. The absolute golden rule here is that R*I is mathematically exactly the same as asterisk parentheses R plus I. You take the base address, jump forward I steps, and extract the value. Arrays are literally just pointers playing around in a contiguous block of memory lockers. Mind-blowing, right? So let's lock in everything we've explored today with these core actionable takeaways. Number 1, always initialize your pointers. An uninitialized pointer holds a completely random garbage address, and using it is a recipe for pure chaos. Number 2, match every single malloc with a free to prevent those nasty memory leaks from taking down your whole system. Number 3, just remember that arrays and pointers are basically identical twins. Array indexing is just pointer arithmetic in a trench coat. And finally, number 4, after you free a pointer, get into the rock-solid habit of setting it to null. That prevents you from accidentally trying to open a freed locker later on. Look, by mastering pointers and dynamic memory, you really aren't just writing basic code anymore. You are directly manipulating the actual physical memory of the machine itself. It completely removes the training wheels and hands you total uncompromised control. So honestly, the only question left for you is, now that you have this incredibly powerful toolkit at your disposal, what are you going to build with it? Thanks so much for hanging out with me for this explainer. I really hope it cleared things up for you, and I'll catch you in the next one.